This is my tracker file showing the water bottle rolling on the surface. I picked a time when I knew that the water bottle had stopped accelerating as my start time, and then chose another time to end before the water bottle went off the screen. I placed my axes at the center of the water bottle cap, and since my water bottle was moving towards the left, I had to use the negative x-axis. My calculated velocity came out to be negative 0.303 meters per second, and the velocity is negative because my water bottle was moving in the negative direction. If I had flipped my axis and made the direction of my water bottle the positive x-axis, then my water bottle would have had a positive velocity. The negative and the positive signs of the velocity indicate the direction of the movement of the object in relation to the positive direction. I could have used any axis for my water bottle, even the y or z axes. If I had used the y or z axes, I would have had to use the magnitude of the vector in the y and z components of the vector velocity vector. Regardless of the axes, the magnitude of the velocity never changes. This graph shows my plotted data from the tracker file and the Python file. The values for the experimental graph were taken from the tracker file, and the data for the model graph were calculated using the Python code shown here. From this part of the code, I have used a while loop to calculate the position of the water bottle as time advances. In the first line shown here, I have set the net force vector equal to 0. This is because at constant velocity, the net force is equal to 0 as shown by Newton's second law. Since there is no change in velocity, the velocities cancel out in the equation to become 0 on the left side. And in order to make the equation true, the right side has to also equal 0. Since the mass cannot equal 0, and delta t cannot be 0 because there is a time change, the only way to make the equation true is to make the net force equal to 0. The second line of code predicts the ball's velocity. The original velocity was calculated using the formula final velocity minus initial velocity divided by the change in time. That velocity was set as ball.vel, and the Python code then used Newton's second law to find the new velocity at a new time interval. Then, each new velocity was inserted into the position equation to find the position of the ball at each time interval, and that data was graphed here. To find the ball's original velocity, I first found the data points that I needed, and then chose a time interval for which I would calculate the ball's velocity. From the tracker file, I used the first two time intervals, time is equal to 0, to time is equal to 0.33 seconds. I also then found the observational time, which was time is equal to 0, the ball's initial position, which was at 0.009 meters, the ball's final position at negative 0.001 meters, and from there I calculated the final velocity. The formula shown at the bottom shows the calculation for the velocity, which was then inserted into the Python code to calculate the position of the ball during the designated time interval. One thing that we have to realize is that when we say that the net force is equal to 0, we are not stating the number of forces that are involved in the movement. From just looking at the object, we cannot estimate the number of forces that are involved in the motion. Imagine that you are in a dark room and an object with a light bulb on it is moving at a constant velocity in one direction. From just looking at the light bulb moving, it is impossible to tell what type of forces could be acting upon the object. So, from Newton's second law, we know that we have to set the net force equal to 0.